mountains or hilly regions. Seoul, as you can see, Seoul, Busan, Daegu, and Gwangju are the major cities in South Korea, and Seoul is the capital of South Korea. According to QS World Ranking, SNU ranks 31st in the world and 6th in the Asia. Before entering into PhD, I was working as a research fellow in Nanyang Technological University (NTU) in Singapore. The location of Singapore is the southeast of to India, and there are only few universities which includes NTU, NUS in Singapore. NTU also holds a very good rank in the world, like 15th and 3rd in the Asia. So I given the link for the PhD admission, those who are interested to acquire PhD admission in these universities. So coming back to our country, in India, there are research centers available in India, such as universities. There are 56 central universities, state universities, deemed and private universities. There are 39 CSR labs and 20 DST labs, and institutes like IITs, ICER, and NITs also there, which one could have obtained their master's or PhD in engineering or basic science as well. So my topic of research or the talk is related to nanomaterial. So I would like to share one one video clip which is highly recommended to see. I hope with this video you have idea about how big or small we are, and how is the nanomaterial compared to the other scales like the universe or the human body, or the if you go to femtometer or smaller scale. So nanomaterials are the materials that have a structural component smaller than 100 nanometer in at least one dimension. So as you can see in the scale, we can see from the 1 angstrom to 1 centimeter. So from 100 nanometer to 1 centimeter, light microscope can work, and we can visually see these particles in this range. But below 100 nanometer, we cannot see with the light microscope. We have to use electron microscope. So the properties of nanomaterials become different from the bulk. For example, a bulk particle with a volume of 1 meter cube and a surface area of 4.8 meter square, and with the same of nanoparticle with the volume of 1 meter cube have the surface area of 4,836 square kilometer. You can imagine it is like few hundred times more than the bulk material. The property of the nanomaterial varies. For example, in this case, surface area. So, what are the types of nanomaterials? Depending on the dimension, zero-dimensional nanometers are there. For example, cluster quantum dots. One-dimensional nanometers, for example, nanorods, nanowires, or carbon nanotubes. Two-dimensional nanomaterials, that is, nanosheets or graphene, etc. And three-dimensional nanomaterials such as polycrystals. So the properties of nanomaterials vary from the bulk materials as I explained. For example, the first, high surface area, higher surface to volume ratio than bulk materials. This enhances absorption, catalysis, and energy storage capabilities of nanomaterials. Second is the quantum effects. At the nanoscale, quantum confinement influence optical and electronic properties of the materials. For example, gold nanoparticles appear red due to size-dependent changes in electron oscillation. Third is the mechanical strength. Nanomaterials like CNT, that is carbon nanotube, exhibit exceptional strength and flexibility used in lightweight, high strength application. The next is the thermal and electrical conductivity. Materials like graphene have extraordinary electrical conductivity due to localized pi electrons, which can also exhibit reduced thermal conductivity in some cases, beneficial for the thermoelectric applications. Next is the catalytic activity. High reactivity of nanomaterials are due to the exposed active site. For example, metal nanoparticles used in fuel cells. And the last is the optical properties. Nanomaterials interact uniquely with light, leading to phenomena like plasmon resonance in metal nanoparticles, enables application in solar cells and sensors. You can see from this comparison chart, the property enhances few times, few hundred times in some cases or some properties compared to the bulk with nanomaterials. So for the synthesis of nanomaterial, there are two types. Like the we can two approaches. One can go from the top down or the bottom up approach. What is top down? From bulk metal, we can cut or make it the smaller particles, and we can go to further decrease in the size, and we can come to the nanomaterial scale. On the other approach, we can start from synthesizing the nanomaterials from the atoms, which can agglomerate or the form the clusters, and then finally we can assemble or synthesis nanomaterials. The basic characterization of nanomaterials are physico-chemical characterization such as structural, optical, electrical, or magnetic properties. For example, structural morphology can be seen in SEM or that is scanning electron microscope or atomic force microscope or scanning tunneling microscope STM, these techniques. And the crystal structure can be determined from X-ray diffraction, that is called XRD, and also transmission electron microscope, that is TM. The composition of nanomaterials can be diagnosed or analyzed from EDS, that is energy dispersive spectroscopy, or XPS, X-ray photoelectron spectroscopy. Likewise, the optical properties can be studied with PL, FTIR spectroscopy, and Raman spectroscopy, whereas electrical properties can be studied with the help of four-probe measurement and Hall effect. And lastly, magnetic properties can be studied with the help of SPID, that is superconducting quantum interference devices. So with this technique, we can characterize nanomaterials, and then we can apply as per our requirement or as per our wish. So We can see there are a lot of application nowadays of nanometals in various areas. For example, biomedical research, healthcare, environmental protection, energy sources, agriculture and food, consumer goods, construction, smart cities, or electronics, machines, etc. Particularly, my research or the topic of research is related to the energy related application. So I will talk more about the energy related things. So the global issues and remedies. There are many global issues such as climate change, air pollution, water pollution, resource depletion, deforestation, waste management, and energy crisis. By developing sustainable nanomaterials, renewable energy solutions, and energy systems for environmental remediation, can directly contribute to mitigating these global challenges. Use of nanomaterials or nanotechnology and their energy-related applications align with the need of innovative technologies that support sustainable development and environmental protection. That is, use of nanomaterials or nanotechnology is one of the solutions to solve these global issues. So, particularly talking about energy-related application, there are few types of energy storage devices such as rechargeable batteries, supercapacitor, and fuel cell. Rechargeable. I think the previous few guests like Dr. Tamboli and Dr. Mahmood about some introduction about and their research related to lithium ion battery and the supercapacitor. So I will go shortly or quickly with this introduction. So rechargeable battery is a kind of energy storage device which have uh, two component anode and cathode as a electrode and it which is separated by the separator and there is electrolyte in between these two electrodes which helps to migrate the uh, charge carrier from one end to another end or the anode to cathode or cathode to anode vice versa. In supercapacitor the phenomenon is different. There are two electrodes. It can be symmetric or asymmetric and the charge storage mechanism is different from lithium ion battery or the rechargeable battery in the case of supercapacitor. And in the case of fuel cell, the hydrogen gas and oxygen gas are used to uh, uh, to get electricity, and the byproduct of this fuel cell is water, which is very environment friendly and which is very good for this high energy related application. So talking about history of rechargeable batteries, battery concept is not new. It has been decades has been known the basic phenomenon of the rechargeable batteries. For example, lead acid battery, nickel cadmium battery, and there were few investigations or the improvement done with the sodium ion. And CIA has been used the rechargeable batteries in medical community in heart pacemakers and then it was followed by the significant research has been done with by the professors Whittingham, Yashiro, and Goodenough in 1980s, which remarkably progressed this rechargeable battery field. And then recently, one we can see that Tesla has been already successfully demonstrated that in one charge 300 miles of this electric vehicle car can go with one single charge. So in 2019, the Nobel Prize in Chemistry goes to the lithium-ion battery development for these three scientists, Professor Goodenough, Professor Whittingham, and Professor Yoshino. So talking about the rechargeable metal ion batteries, lithium ion battery dominates the day-to-day life applications or uh, the major part of the lithium ion battery. So what are the lithium ion battery or the energy storage device? As I explained, it is the conversion of chemical energy into electrical energy or vice versa during the charge or discharge. One can see the commercial batteries in this form, for example, in cylindrical or the square shape. The typical battery component are anode and cathode, which is separated by the separated, and it contains the electrolyte. So one could surprise with these numbers like okay, what is 18650? This is called 18650 battery. One can see this number, but we might be surprised like okay, what is the number? Now I can show you this demonstration for the numbering. Like for the first two digit, 18 is the minimum millimeter is the diameter of this cell, 65 is the length of the cell, and 0 is the cylindrical design number. So that's why it's combining. It is called as 18650 cell. So one can connect battery to increase the volt in series. For example, 3.7, 3.7, 3.7, we can get the volt 11.1 together. And if you want to increase the current, we can connect these batteries in parallel. For example, if we connect these two batteries, then it can go to like it can multiply in the numbers as we connect in parallel. So the simplest form of lithium-ion battery is the coin cell. So as I explained, the number 2032 is the first two digit are the diameter of the cell, and 3.2 is the length of the cell. So typically the coin cell contains these components, but the basic part is the same, like anode and cathode, which is separated by the separator. But due to this safety issues, one can use this gasket and the casting top and the spring to make it more safe. So how performance are the what are the performance evaluation parameters for the battery? That is how much energy can I store? In the limited volume, it is called as energy density, and it is limited weight, it is called as specific energy. How powerful battery is? It is the evaluation is calculated in terms of C rate or the power density, and how efficient battery is can be evaluated in terms of voltaic efficiency or the coulombic efficiency. These parameters are based on thermodynamics and kinetics of the particular electrochemical reaction. So I would like to quickly go to the storage mechanism of lithium-ion battery, typically lithium-ion battery. As I explained, there are two components like anode and cathode. So the simplest lithium-ion battery demonstration is with the graphite and the as an anode and lithium cobalt oxide as a cathode. So during the one can see the charging out or the discharging mechanism. During discharging, what happens is the lithium ion migrates from the anode to cathode and intercalate in this lithium cobalt oxide. So the mechanism can be predicted like this: cobalt oxide plus electron gives lithium cobalt oxide. So this process is the reduction of the cobalt, and on the other side, lithium LiC6 forms the graphite plus lithium plus electron, and electron completes the its path through the external load or the whatever device we connected through this battery. And on the other hand, or the other process, that is the non-spontaneous process, that is once our battery is discharged, we every day we connect to the charger and we charge it again to the normal state, right? So what happens inside this during the discharge process inside the battery? There are few steps. As we can see, in the first step, oxidation happens from the solid state diffusion in the bulk of the anode of lithium happens. At the second step, dissociation at the anode or electrolyte interface happens. And at the third step, the transportation through the electrolyte of these lithium ions happens. And in the fourth step, the insertion at the cathode electrolyte interface happens. And in the last step, diffusion in the bulk cathode happens. That is the called as reduction. So at this stage, like the at the current collector stage, one can see that lithium can come in through or the migrate through this conducting carbon or the carbon black, and the source of the electron is here current collector, which provides the electron. And from the external circuit, the load if the load has been connected or the whatever device like mobile or anything laptop, it can work through this external circuit through the pass of the electrons from one end to the another end. So this is the storage mechanism of lithium battery. So one could wonder how to calculate the specific energy or the specific capacity, and how one can determine which is the best material for the battery, and how to choose the battery materials for testing or the application, for example. But it's very important to see that the energy levels of this material, where it lies, and it highly depends on the basic criteria of this choosing the battery materials is the electrode potential. For example, the electrode potential of this lithium cobalt oxide lies about around 3.9 versus lithium potential. So, what is the total voltage of the cell is the voltage of the cathode minus voltage of the anode. For example, in this case, if we take the voltage of the cathode of lithium cobalt oxide, which is 3.9, and on the other hand, if we take the graphite, which has very low potential versus lithium zero point 0.2, so the difference of this cathode and anode is 3.7, which is the total voltage of the particular cell if we combine graphite and the lithium cobalt oxide. Okay, so now how to calculate this specific capacity? Specific capacity is very simple. We can multiply this Farad constant with the electrode molecule divided by the molecular weight. For example, if we take the lithium metal, here the number of electron is 1 and the molecular weight of lithium is 7. So if we divide this number, we can get the specific capacity which is very high, 3829 milliampere hour per gram. Similarly, we can calculate on the cathode side the specific energy. Specific energy is nothing but the Faraday constant into total potential of the cell divided by the molecular weight of the electron. For example, if we calculate the if you want to calculate the specific energy of lithium cobalt oxide, so the Faraday constant 26,800 potential of the cell is 3.7 divided by the molecular weight of the nickel cobalt oxide is 98. So it comes the specific energy of the lithium cobalt oxide comes around 518 watt hour per kilogram versus lithium as I know. So one can calculate with these formulas the specific capacity or specific energy of the lithium ion battery. So talking about the, one could be very curious about how the uh, lithium reacts with the another material or the cathode. So there are, depending on the how is the reaction happening, there are types of reactions such as intercalation reaction. In this intercalation reaction, solid state redox reaction happens, and the stability of structure and shape depends on the intercalation reaction, but it has a limitation to this intrinsic capacity. Though intrinsic capacity is the property of the material, we cannot increase at certain point. So many lithium batteries rely on this type of electrode. So the another type of reaction is the conversion reaction. For example, metal oxides like vanadium oxide, chromium oxide, or the manganese oxide reacts with lithium and it forms the converted product. It has high capacity, but it has poor kinetics, and it has large separation of the voltage on charge and discharge. And on the other hand, there is alloying reaction in which the silicon, for example, silicon or the tin or the aluminum reacts with lithium and it forms composite. And but it has high capacity, but it has the disadvantage like large volume expansion. In case of silicon, there is 400% of the volume expansion, so which is not good for the battery cycle or the battery life. So nowadays, along with lithium, other metal ions have been explored, such as sodium, potassium, zinc, aluminum, and magnesium, or ammonium ion. My research is a little bit diverted or diversified from lithium, and I focus on mainly aqueous batteries. So there are choice of electrode for the usage or the use of batteries. For example, we can use inorganic electrode materials or the organic electrode material. But compared to the inorganic electrode materials, organic material have its own merits to use in rechargeable batteries, such as they are cheap, they are abundant, and they are less toxic. For organic materials, there has been many strategies we can use to increase the capacity or the voltage or the cycling stability or the rate performance of the batteries. And there has been many design strategies has been used for the application in batteries to increase their electrochemical performance, such as the increase in the number of active sites or the reducing the molecular weight or incorruption of heteroatoms. There has been many factors such as the dihedral angle between these organic molecules also imports the or the affects the starch or its performance or the total capacity of the batteries. But there is a lack of systematic investigation of functionality tunings in organic materials for the study of reversible lithium-ion storage mechanism. So here we go. Covalent organic frameworks is the solution for these organic materials to make it versatile or the as per our choice. For example, what is covalent organic framework? Covalent organic frameworks are crystalline organic porous polymers made up of lightweight elements, particularly heteroatoms such as boron, carbon, nitrogen, oxygen, sulfur, etc. They are linked together with the by strong covalent bonds and they have high thermal stability. In 2005, Professor Omar Yagi first synthesized the covalent organic framework. So covalent organic framework don't have any metal component or the inorganic part. It is purely organic material. So the reversibility in COP formation can be used to make the framework more crystalline according to our choice or the properties what we intend to do. For example, COPs are the beautiful materials where we can tune or we have a diversified choice to make these structures. For example, there are basic organic chemistry reactions which, with the help of which we can stitch or the we can make together these two organic different molecules and make it in the polymer form and make it more crystalline form. As we can see, there are different type of reaction. For example, boroxine, phenazine, boronate ester, sperine, ship-based reaction, borazine, and nitriles, trimerization of nitriles, Nonagel reaction, beta-ketanamine, Michael addition, imide formation, benzoxazole formation, dioxin linkage, and ester linkages. This type of organic reaction we can use to make or the synthesize COF materials. The beauty of COF here again lies in the tunability that various topology of various kind of COF we can make depending on the application or our choice. For example, honeycomb-like structure or the square or the KGM, HXL, or there are, as we can see here, there are different type of precursors we can use and stitch together and we can make a heterostructure or the COF as per our application. Now here we can control the crystallinity through the reversible reaction formation. First, we can make the reversible reaction, that is the amorphous network, and again we can tune the condition and make it more aligned or the more crystalline form. So it can be arranged regularly. So with this regular arrangement, we can tune the pore size or the porosity, and we can increase the surface area. So basically, with the help of COP, we can design the material as per our choice. We can stitch or we can do molecular engineering, and we can apply to our whatever purpose. For example, in my case, I apply in energy storage application. So talking about COPs in energy related application, COPs has been used in supercapacitor as electrodes, and in metal ion battery also they are used as an electrode. Also they have been used as a separator. So the role of different COF as per their functionality, I reported in this review article, Advanced Energy Material 2022. I use the best. I make the best use of the Corona time, and we write this extensive review on the COF materials used for the electrodes for supercapacitor of batteries. As we can see, there are different kinds of batteries and different components has been different functionality COPs has been used for various applications. Particularly, my research or my interest was developing this hexagon 2D curve. So in my lab at KAUST, with the help of other colleagues, I have developed a series of hex azov curve. For example, we can use the skip based very simple reaction, ketone and amine reaction, and we can make the phenazine like structure, and we can modify the structure according to our final purpose. For example, as you can see here, benzene tetramine I used, but in other case we can stitch these quinone molecules, diquinone. So we can make it very interesting structures, and we can make the extended structures also with the large pores or the more number of redox active site. Also, I can discontinue this conjugation and make use the flexible structures, and I synthesize the other hexas of COP4. And finally, with the different keto, for example, pyrene tetraone, with the help of this hexaamine, I synthesize this novel HATP PT phenazine or hexazap. As you can see, this COF has been explored for various different rechargeable battery applications. For example, first COF has been used for zinc ion battery, second is zinc, ammonium and magnesium ion battery, third COF used for zinc ion battery, fourth is the potassium ion battery, and the last one used for ammonium ion battery. We time to time reported these all works in these quoted journals. So, as I explained you, the synthesis of this cough is based on the keto and the amine precursors, and we can stitch or the make the different cough. So the basic characterization of the cough is the powder X-ray diffraction pattern. So, as I explained, you cough are the crystalline material, but the arrangement of this cough is also important. For example, in case of this hexaza 1 cough, the arrangement is different. That is A eclipse. That is eclipse means 1/1. It is perfectly eclipsed and it has a accessible pore. And in other case like hexaza cough, the cough structure is slightly inclined. I mean the second layer is inclined. As you can see, the simulated XRD pattern matches perfectly with the incline. And in the third case, uh, the first layer is uh, the cough which is formed has the arrangement of ABC staggered, which is not at all eclipsed. So it has slipped or the disordered structure. So the I mean the successful synthesis of this cough has been demonstrated from the FTR spectroscopy, and it has been also supported by the data from 13 carbon C solid state NMR analysis. So talking about my first work, as I explained, this hexaamine is reacted with this tetraketo, and I can make the HATP PT curve, which has the this phenazine type of redox active site. So I did the basic physicochemical characterization, and it shows that this experimental PXRD matches with this simulated AB structure. This is not perfectly A eclipse structure, but this is like slip AB structure or the staggered AB structure. And the successful synthesis or the completion of reaction has been supported by the FTIR and the solid state NMR data. So this cough has been used for aqueous ammonium ion batteries. I don't want to go in detail about the what are the techniques or the electrochemical techniques. Yesterday or the before also few guests already explained about these techniques, CV and the basic electrochemical characterization. So I would like to go about directly the work. So when we try to check this cyclic voltammetry of this HATP PT cough in ammonium trifluoromethane sulfonate, we see that HER happens. HER means hydrogen evolution reaction. HER is unwanted reaction. It means it's the formation of hydrogen gas or the bubbles in the battery. So it's unwanted because these bubbles interfere with the rate performance or the long-term cycling stability. So how to solve this problem of this severe HER? So we find one solution. Adding sucrose molecules would break the hydrogen bond between the water cluster. thereby inhibiting the proton migration to suppress this HER terminally. So once we add this sucrose small amount, we could control or we could minimize this unwanted HER reaction. So now we finalized the electrolyte with the addition of sucrose, and we investigated the further electrochemical characterization. So we investigated in detail the rate capability of this electrode material, which is very good. And then we performed galvanostatic charge discharge. As you can see here, galvanostatic charge discharge gives the moderate specific capacity for this ammonium ion battery. And one can see that compared to the other reports, we are in good position in terms of specific capacity or in at the corresponding current density. And one could be surprised that how this reaction or the how this ammonium is interacting with this cork material. So we investigated in detail that what is the is there anything what is the dominant character for this intercalation or this capacitive behavior of this ammonium with the cork. So we could find that the B value is more than zero point 0.8, which means that this charge storage or the uh, charge storage happens through this intercalation or de-intercalation process, and the ammonium ions prefer to react at the surface or the near the surface without a sluggish long-range solid-state diffusion process, which achieves fast ion diffusion kinetics. So no surprise, due to this fast kinetic, we could achieve 20,000 cycles for this ammonium ion battery, which is very good. And that time it was the first report which could demonstrate that 20,000 cycles for the ammonium ion battery. Here you can see that Coulombic efficiency also very good, around 100%. And compared to the other reports, our COF work also outperforms in terms of the current density and capacity retention. We checked the Raman spectroscopy and we could see that after 20,000 cycle also the Raman spectra intact. It means it has very good stability in terms of the structural properties. So now it is very important to see how the reaction happens or the how the ammonium is interacting with the COF. So what we did is we take the 3 point. Point one is the charge point, point two is the fully discharged point, and point three is the charge again. So what happens during the charging? De-intercalation of ammonium happens from the COF, and during the discharging, intercalation of ammonium into COF happens. It means that ammonium is intercalating in the COF during discharge, and again during the charging, the intercalation of ammonium from COF happens, and this cycle repeats on. So what we did is we collected these 3 points and analyzed XC2 FTR spectroscopy. So this peaks from this one could see this FTR spectroscopy and the characteristics peaks for the CN and C single bond and C double bond N, and in the other region NH N bond and NH bond. So during charging point one, de-intercalation of ammonium happens. And as I explained, during the discharging, intercalation of ammonium into COF happens. And again, during the charging, de-intercalation of ammonium from COF happens. So what is the conclusion of this slide is C double bond N are the redox active site center and will be broken to form C single bond N during intercalation process of these ammonium ions. And also, on the other hand, there is hydrogen bond formation between ammonium ion and nitrogen atoms in discharge process. So we were more interested to see, okay, this is the only one technique we used, and if we can prove with the other techniques. So very interestingly, we did in situ Raman spectroscopy, and these results also strongly supports our hypothesis that uh, the reversible change of C double bond N and C single bond N happens during the charge storage mechanism, that is the discharge on charge of ammonia into COF happens. So with this experimental proof, by combining ex situ FTR and in situ Raman spectroscopy result, we propose the coordination process of ammonium ions during the discharge process into COF. So when one ammonium ion coordinates with nitrogen atom, one free radical is formed on the carbon atom while C double bond N is broken. Likewise, after the second ammonium ion coordinates with nitrogen atom, another free radical will form. Therefore, those two negatively charged nitrogen atoms apart from each other to form one C double bond C bond. Such transformation from C single bond C bonds to C double bond C bond during the intercalation process of ammonium ions is validated well by the reversible change of these peaks in Raman spectroscopy also. So now coming back to the device or the electrochemical characterization, as you see the COF performance in the negative range uh, as compared to the saturated calomel electrode. So COF is used as a negative electrode, that is anode. Now on the other hand, we want to use the other electrode as a other electrode means cathode and different material. For example, we choose here copper hexacyanoferrate as a cathode, which perfectly match with this COF window. As you can see, as you could see here, the copper hexacyanoferrate acts as a cathode, and when we combine this COF as a negative and copper hexacyanoferrate as a positive electrode, we could achieve total cell voltage around 2 volt, which is designed for this ammonium ion battery, and we can check the rate performance, which is decent also, and we could achieve 20,000 cycles with the cooling efficiency around 100%. And compared to the other ammonium ion work, our work outperformance with the recent reports. Finally, for practical application, we demonstrated pouch cell. For example, we combine this COF and hexacyanoferrate together with the in between separator and the outside is the plastic film, and we assemble this pouch cell. And surprisingly, or the with the surprisingly, we could see that this cell also performance or shows at very low temperature of minus 20 degrees C, also at room temperature. So this is just proof of concept that this battery works at very low temperature also and at room temperature also. And last year we submitted this work and published in this journal. So now moving to the next work, similar hex as of COF we synthesized, which has a lot of redox active site, that is phenazine site, which is the active site for the charge storage carrier. For example, in this work, we reported this COF for the zinc ion battery as a cathode material. As you could see that the basic electrochemical characterization shows that this electrode material or COF acts as a cathode. And similarly, we are interested to see what happens and where is the redox active site. And we could prove that from the ex situ solid state NMR and XPS analysis, C double bond N is the redox active site. And with the simulation, we could systematically investigate or the prove that 18 zinc ion can be intercalated or react with the 1 unit of this PA. And finally, we demonstrated the full device and check their electrochemical performance. Here, I would like to show one uh, video clip for the demonstration of this LED for this battery. So we successfully demonstrated this battery, and we show that the LED is blown up. In the following work, we used two COP material, that is hex as a one COP and hex as a two COP. What is the difference between these two COPs? So this is the beauty of COP. As I explained, we can stitch or we can do molecular engineering of the COP, and we can design materials as per our choice. For example, here the phenazen or the nitrogen, I mean, these heteroatoms are active redox sites, but we wanted to stitch or to make the quinone moieties in this framework. So we start with this tetraamine with which contains diketone, and we reacted with this hexaketocyclohexane, and we could get the two different COF exactly with the presence of this diketone or the quinone and without any quinone. So we could compare between these two COF. And as we expected, we applied these two COP materials for as electrode as a cathode for zinc ion battery. And as we expected, we see that this quinone and nitrogen, these two uh, sites, redox active site, can enhance the performance of the battery. And you can see the in this graph C, the performance of this COF2 is much better than the COF1. We did a lot of in situ or ex situ characterization for this work also, and we simulated and proposed the mechanism step by step, the how the zinc ion storage, charge storage happens, and in the systematic way the six step zinc ion intercalation happens, and the uh, charge storage mechanism is demonstrated successfully. We reported this in 2021. So coming back to this quinone containing cough, my interest was to check with the other aqueous batteries except the one which we used as a zinc. Now again, I used this cough for the aqueous ammonium ion battery. In this work also, we demonstrated successfully that the ammonium uh, ion can interact with this quinone and nitrogen molecule through the formation of hydrogen bond. One can see, or if interested, I don't have time to go in detail for this all charge storage mechanism and the how we approve this charge storage mechanism in this uh, cough. So I can quickly show that the ex situ FTIR and XPS analysis proves that the charge storage happens through this C double bond O and C double bond N or C single bond N atoms or the redox active site. We reported this work in 2021. So with the same curve, I was interested to further explore the other aqueous ion batteries. So now we started with the magnesium ion battery. Here also the charge storage happens in the similar way with these two steps. Like in the first step, 6 magnesium ion reacts, and in the second step, 6 magnesium ion reacts. So total 12 magnesium ion reacts. Surprisingly, this COF in magnesium ion battery works in both window, and we could design or we could assemble this symmetric battery, and we demonstrated successfully the device with this magnesium ion battery, which shows very good cycling performance and electrochemical properties with the rate capability. In 2022, we reported this work. So this cough is also very interesting because it has disconjugation, but my idea is to use this disconjugation means this is flexible structure. So flexible structure can what is the effect of this charge storage or the mechanism on this flexible structure? So we demonstrated that the competitive proton and the potassium ion, how it interact with this cough, and we successfully demonstrated XC2 characterization, for example, XPS or NMR, and we prove that the charge storage happens with these redox active sites. And the systematic investigation we did, and we simulated the structures and we demonstrated the charge storage mechanism in detail. Here we also answered one very important problem, that we suppress this HER, that is unwanted HER reaction, by tuning the electrolyte or the electrolyte composition. One can, if one can interested, you can see this report we reported in ACS Nano in 2023. So, talking about the summary of this work, as we can see, I synthesized this series of hex as a cough. For example, cough 1, 2, 3, 4, and HATP cough. As I explained, I use this cough for various applications. For example, zinc, ammonium, magnesium, proton, potassium, and ammonium battery. So moving to my PhD work, I work on carbon-based nanomaterials. Maybe Dr. Mamane yesterday explained the why we work on carbon materials. So I don't want to go in detail about the introduction of the carbon materials and its importance. So in my PhD work, I applied for energy storage and conversion application. For example, in energy storage device, I use supercapacitor, and in the conversion application, I used oxygen evolution reaction, that is OER. So in the first case, I synthesized the sulfur modified graphitic carbon nitride nanostructure as electrocatalyst and used as a oxygen evolution reaction electrocatalyst. And we demonstrated this sulfur modification can enhance significantly this OER performance, which is good. At that time, this was the first report in carbon-based system, which has a very high current density and very low over potential for this OER reaction. In the second work, what I did is I take the pre-synthesized MOF material, that is ZIP8, which contains zinc. As we know that zinc can directly sublimize at higher temperature. So my idea was to make use of this sublimation technique. What I did is I wrapped this oligomer, which has this nitrogen, phosphorus, and uh, moieties in this oligomer. So I wrapped this oligomer on this zip 8, and then heated this at high temperature. And surprisingly, and as per my idea or analogy, by tuning or the increasing the thickness of this oligomer, one can tune the pore size or the porosity of this material, which is the outcome of this product. For example, this, as you can see from TM images, this is highly porous structure. And then I could scale up this reaction to gram scale. My Korean professor, Professor Tagwanan, is very famous in synthesizing metal oxide or various nanomaterials and their scale up. His iron oxide nanomaterial synthesis on large scale is a milestone achievement in nanomaterial technology or nanomaterials researchers. So in my lab, I large scale during my PhD this porous carbon material in at something around like 1.4 gram, and we demonstrated this uh, porous material as an electrode for supercapacitor, which demonstrated or which showed very good capacitance values. So this is all about my talk, and I would like to just go quickly to my pre-PhD works in NCL in India, uh, which uh, which is mainly based on the nanomaterial synthesis and their various energy related application. And when I moved to Singapore, also I continued the working on nanomaterials for various energy application as well as other technique. And in my PhD, I focused on heteroatom modified carbon nanomaterials for their application in water oxidation and supercapacitor. And finally, in my research work at KAUST, I focused on synthesizing porous materials such as KOF and their energy related application. And time to time, we reported these materials. So, in conclusion, nanomaterials are not only beautiful in their structure but also transformative in their application, driving advancements in energy and sustainability. So, thank you, and I would be very happy if I could help you. Thank you very much.
Thank you, sir. Uh, Participants, from your side, if you have any questions, you can ask, sir. Shelar, sir.
Uh, some participants have raised their hands, like Jyoti Mane madam and Shivlila Maitre madam. If you have question, you can unmute your mic and you can ask your question. Participants can unmute their mic and can ask their question, or they can also write their question in the chat box.
Hello? Hello, Patil sir?
Participants, is there any related you want to ask? Feel free to ask.
Dr. Vinayak,
Yes, sir.
hello. I have one query.
Yes, please.
When you talk with the fuel cell, no? Uh,
Yes, sir.
in the fuel cell, hydrogen oxygen fuel cell.
Yes, sir.
So, whether the real applications of hydrogen oxygen fuel cell is started somewhere.
Uh, Yes, sir. It's not like day-to-day life it's using now, but it has been demonstrated successfully. The problem with the hydrogen is the storage, because hydrogen is very explosive gas, and we need the heavy cylinders and very major safety protocols to follow our storage of the hydrogen. So in day-to-day life, it's still very challenging to make use of hydrogen as a cylinder to use fuel cell in electric way, I mean the vehicles or something like the real life application. But the research is going on. For example, we could, if we could store hydrogen in some porous material, and if this is the safer alternative, we can use this material and we can use in fuel cell.
Yes, yes, yes. So the during the Dattakumar Mamane's talk, he has explained how that hydrogen production and all that.
Yes,
So
sir.
so that's why I was query that hydrogen storage is the problem, and that's why in day-to-day
Yes,
life it may not be in soon. Okay, so
Yes,
but
sir.
somewhere in restricted applications it might be available, no?
Yes, sir. If there is no safety related issues, for example, in lab scale or the industry scale, it's fine.
Okay, okay. And one more very important information you have given, that the research opportunities in Singapore, or even I think your link given of the Singapore.
Yes, sir. Singapore, Korea, or the actually due to the limit of time, I could not. I mean, I planned to make it, but I
Yeah.
limited myself. There are
So,
a lot of
our,
opportunities inside India, outside of India also.
yes.
So one could be interested, then they can reach me out, or it's very easy to Google it. There are many fellowships in Western countries, also in Korea for PhD, postdoc.
Yes, yes, yes. So that's why our participants may take benefit of your guidance regarding this PhD opportunities overseas, and also is there any
Yes,
funding, government funding for the research in particularly material science?
yes, sir. There are always funding, and I could say nowadays material science is interdisciplinary, and there is a lot of opportunities and funding in almost very, I mean, developed countries. For example, Korea, US, Singapore, even right now in Saudi Arabia also. Yeah, there is
Yeah.
a lot of opportunities now in material science.
Okay, sir. Okay. So very nice to talk with you. After a long time, we have been actually thanks to the technology that we could connect uh,
Yes,
from your place, South, that is Saudi Arabia, and
yes,
after a long time we could meet here virtually. So thank
yes,
you
sir,
very
yes.
much. So if the participants are not having any question, so I would like to thank officially as a vote of thanks part of the this presentation. So thank you, Dr. Kale, for your timely accepting our invitation and giving us such a nice presentation, and also guided for the research purpose. Thank you. And your PPT will be, if you share, I will share to the participants.
Sure,
Uh,
sir.
yeah. And there is, sir, one query from, means I want to ask about the your today's presentation. Your today's
Yes, sir.
presentation. Uh, we need to, means, send the recording. So is there any problem, sir?
No, no problem, no problem. You go ahead,
Okay.
please.
So this recording session we have to send to our AICT ATAL formalities to be completed, means the report for
Sure,
pending and all that. So it is to be uploaded on the YouTube. So participants will also get that. Okay, sir. Thank you, sir.
sure,
Thank you
sir.
very much. See you
Thank you
again.
for the, yeah.
Yes.
Thank you for the opportunity. Thank you
Yes.
again.
See you again. See you again. Thank you, sir. Participants, we will take a just a 5-minute break. At 3:30, our next session will start. Our next session will start. Don't leave the meeting. Don't leave the meeting. Be logged in only, and we'll soon start the next session of Shekhar Jeurkar, our industry expert, Shekhar Jeurkar. He is going to uh, join us second time. After first day, he is going to join us the second day. So our session number 12 of engineer Shekhar Jeurkar, a consultant in the material science. So logged in, don't leave the meeting. Soon we will start. We'll take a 5-minute break. Our resource person, Jeurkar sir, will join soon. The feedback link of this session, means Dr. Kale's session, is already sent in the chat box. All are informed to fill this session feedback. Today, there are three sessions. One is over. Now we will take the feedback of each session separately. Remember, today at 6:30 we will be having the conclusion of this FDP. So up to uh, 6:30 there will be sessions, and at 6:30 a virtual feedback will be taken, and then the validatory function, and simultaneously there will be our online test on Atal portal of your login, Atal portal login. So all these to be happen today. Today is the last date. So be patient and take the benefit of last day of this FDP. So stay tuned. We'll join soon. Welcome, Jeurkar sir. Good afternoon, Jeurkar sir. Good afternoon, sir.
Good afternoon. Can
Yes,
you see me?
Yeah.
Okay. Is
Shall
it
we check?
audible?
Yeah, you are audible, and we'll check, sir, whether your
Yes.
screen or PPT will run or what.
Okay.
You are now meeting host. You can share.
Yes, is it visible?
Yes, sir. Yes.
Okay.
PPT mode, if you slideshow mode.
Yes.
Yes.
Is it okay?
Yeah, okay, sir. Okay. So we will wait for another 2 minutes
Okay, sir.
and we'll start.
Okay, sir.